Welcome back to AI Papers, a deep dive. No press releases, no secondhand summaries, just the paper itself and the honest critique. All right, let's dig in. Here's a scene from inside an AI training run. You hand an agent a household task, cool a bowl and put it in the microwave, and you let it try 8 times. 8 separate attempts, moving through the same kitchen. And over, all 8 of them land in the exact same spot. Same room, same layout, same situation. Common sense says that's one situation visited 8 times. The standard training algorithm says it's 8 complete strangers and throws the connection away. Patch that single blind spot, and a 1.5 billion parameter model jumps more than 20 points in success rate, beating models hundreds of times its size for less than 0.5% of extra compute. Quick heads up before we go further. This is an AI-made explainer, both voices included.
And the part that gets me is how little they actually changed. This isn't a bigger model. It isn't more data. It's the same 8 attempts you already ran, reread. The paper's real claim is that the whole field has been making a quiet modeling error, treating an agent's exploration as a bundle of separate straight lines when the data was a graph the whole time. And this matters because long-horizon agents are the thing everyone's chasing right now. Models that browse, click, call tools, write code across dozens of steps. The bottleneck isn't the model anymore. It's that the reward shows up late and sparse, so the learning signal is thin and noisy. Anything that squeezes more signal out of the same rollouts, basically for free, is a big deal.
So let's start with why that signal is so thin in the first place. Picture an agent taking 40 actions before it learns anything. The environment stays completely silent, no feedback, no hints. And then, at the very end, it hands back a single bit, success or failure. That's it. Now you have to look back at those 40 moves and figure out which ones actually mattered. This is the credit assignment problem, and it's brutal at long horizons. Think of a soccer team that loses 1-0. From the scoreline alone, who do you blame? Maybe move number 3 was brilliant and moves 30 through 40 threw it away. Maybe an early blunder doomed everything and the rest was fine. One number at the end has to be smeared back across every decision, and a great early move and a terrible one can land on the exact same failure signal.
Right. And the tool the field reaches for here is GRPO, the method most of these reasoning and agent models are trained with. Its trick is genuinely elegant. Normally, you'd train a second neural network, a critic, whose only job is to score how promising each situation is. Expensive, fragile, a whole separate model to babysit. GRPO kills it. Instead, it just samples a group of attempts, say 8, at the same task, and scores each one relative to the group's average, grading on a curve. The group is the baseline, no referee needed.
And that grading on a curve idea is exactly what G2PO inherits and then pushes further. But there's a wrinkle in how people applied it to agents. Cramming all 40 steps of a trajectory into one training sample blows up your memory, so the field moved to step-level training. Treat each observation and action moment as its own little sample. Lighter, cleaner. But baked into that move is an assumption nobody examined.
The assumption being that every attempt is its own private universe.
Exactly that. Trajectory 1 is a line. Trajectory 2 is a different line. They never speak to each other. So when your 8 attempts all pass through that same kitchen state, each one estimates how good that state is using only its own single run. Even the closest prior method, GRPO, noticed that identical states recur, but it still judged each state from one trajectory's outcome, and it still only compared moves against their immediate local neighbors. Those are the 2 cracks G2PO drives straight into.
So the natural question is, if you can see that the lines overlap, what do you actually do with it?
You stop drawing lines and draw a map. This is the whole paper in one picture, and it's worth watching it form on screen. Take your 8 trajectories. Every time two of them land in the identical situation, same web page, same kitchen state, same database, you fuse those moments into a single node. The actions become arrows, edges, running between nodes. What was 8 parallel lines collapses into one branching graph that shows the real structure of how the agent explored. And here's the airport version of it. Imagine 8 travelers each rushing through the same airport to catch flights. Treat each journey separately and you've got 8 little stories. But overlay all 8 onto one terminal map and suddenly you can ask a far richer question. Of everyone who passed through gate B17, how many actually made their flight? You couldn't ask that from any single traveler. You can only ask it from the map.
I want to flag one thing right at the top, though, because it's going to come back. This entire payoff depends on those overlaps being real, on the agent genuinely revisiting the same situations often enough to pool them. When states collide constantly, the map is rich. When they almost never collide, the map is just your 8 lonely lines again with extra steps. Hold on to that, because the hardest benchmark in the paper is exactly where it gets tested.
That's the honest tension, and the paper does check it. During training, the typical shared node pools about 5 attempts, and only around 12% of WebShop steps, 8% on the household tasks, are singletons that nobody else ever revisited. So for the clean benchmarks, the overlaps are real, not wishful. Now, once you have this map, 2 things become possible that simply weren't before, and they line up one-to-one with the 2 cracks I mentioned. Crack 1 is high variance value estimation. If you judge a situation by the single trajectory that wandered through it, you're at the mercy of luck. A run from a genuinely great position might faceplant later and make that position look worthless. A run from a hopeless spot might get rescued and make it look brilliant. It's like rating a restaurant from one visit. You might have caught the kitchen on its worst night.
And the fix falls right out of the graph.
It does. A node's value becomes the average outcome of every attempt that passed through it. Visit the restaurant 8 times, and the bad night washes out. There's a clean mathematical result behind this. Pool the samples in a node, and the noise in your estimate drops in proportion to how many you pooled. Gather 5, the variance roughly fifths. And because these tasks are sparse reward, nothing until the end, the value of any midpoint situation just collapses to the eventual win rate of everyone who reached it. So a node's value is, almost literally, a chess position's value. The fraction of games that reached this spot and went on to win.
And the beautiful part is what that costs. Nothing. You're not training a critic. You're not hand-labeling steps with a reward model. It's arithmetic over data you already collected. The exact same instinct that let GRPO fire the critic in the first place, just aimed one level deeper.
So that's crack 1 closed. Average the situation across attempts, and your value estimates stop lurching around. Crack 2 is subtler, and it's where the real novelty lives. Eric, this is your half.
It is, and this is the densest stretch of the paper. So let me say where it lands before we climb, because the payoff is a single kitchen example where math that should pile up noise instead cancels it out. Crack 2 is myopic credit assignment. Even with good value estimates, the older methods only compare a move against its immediate siblings, the other options available at that exact spot. And that's blinding. You can never tell whether you're rewarding a tiny tweak in a trivial corner or a decisive breakthrough that vaults the agent toward the goal. Locally, both just look like a bit above average for around here. So G2PO changes the yardstick. Every action moved the agent from one node to another. So it has a value gain, where you landed minus where you started. If you've heard the term temporal difference error, that's exactly what this is. Not how high up you are, but how much altitude this one step gained you. Standard textbook quantity. The twist is the reference frame. Instead of comparing that gain only to nearby moves, G2PO pools the gain of every single edge in the entire graph and standardizes against that global pool.
So you grow one shared map instead of 8 separate lines. But how do you actually pick out the move that mattered from that whole pool?
Watch the kitchen example, because it's the whole idea in one frame. The task: cool a bowl and put it in the microwave. 2 moves are on the table. One picks up a cup and carries it to the microwave. Wrong object, off objective, a dead end. The other walks to the fridge, which is where you'd actually cool a bowl, a real step toward the goal. Now, under the old local comparison, that good move toward the fridge scores a measly plus 0.55 because its destination is only slightly above the average of its neighbors. But edge-centric advantage accounts for how low value the starting node was, how much absolute ground this step actually covered, judged against every move in the batch. And the same fridge move jumps to plus 2.1. Watch it on screen. The trivial gain stays flat. The real breakthrough lights up. That's the grading reframe. You're scoring students by how much they improved, and comparing improvements across the whole school, not just within one classroom. A kid who climbed from failing to mediocre made a bigger real gain than the top student nudging from excellent to slightly more excellent.
And the consequence I find genuinely striking. A brilliant move gets credited even if its run ultimately failed.
That's the headline payoff, yeah. It's the poker hand where you make the perfect call and then lose to a lucky river card. Grade purely by who won the hand, and your brilliant call gets buried with the loss. Edge-centric advantage credits the call on its own merits. It lifted you from a weak spot to a strong one, regardless of the unlucky ending. And the mirror image, a lazy filler move that happened to sit inside a winning run, gets correctly marked down.
Now here's the part that should bother a careful viewer. You're subtracting 2 estimated values and then standardizing against the whole graph. Subtracting 2 noisy numbers usually compounds the noise, and a global reference sounds like it should inject even more. By rights, this should be a variance disaster.
It should, and it isn't. That's the genuinely surprising result. The trajectories passing through your destination node share history with the trajectories passing through your source node. They overlap, which means the 2 value estimates aren't independent. They're positively correlated. And when you subtract 2 positively correlated quantities, the correlation cancels variance instead of stacking it. So the paper proves the finer, sharper edge signal stays bounded by the same variance as the crude whole trajectory advantage. You get the discernment of the global view without paying the usual noise tax. The very overlap that built the graph is what keeps the new signal stable.
So let me consolidate, because that's 2 moves done. Average each situation across all attempts to get a stable read on how good it is. That closes crack 1. Then score each move by the absolute progress it made, judged against the whole map. That closes crack 2. And there's a third term they keep around, a plain episode-level signal that just tethers everything back to the final win-or-loss, so the agent doesn't get clever and drift off the actual goal. 2 big ideas, 1 quiet anchor. Both big ones fall straight out of having built the graph.
And I'll just note they keep a 4th, local comparison term too, mostly for completeness. It's the old G2PO style move. The conceptual weight is entirely on those 2. Pool the situation, score by absolute progress.
So does the free lunch actually show up on the plate? The prediction is clean. If pooling really does cut variance and the absolute progress signal really is sharper, we should see faster, cleaner learning. And we do. On the household task benchmark, ALFWorld, G2PO beats GRPO by more than 20 points of overall success rate at the 1.5 billion scale. On WebShop, the e-commerce navigation benchmark, about 14 points of success rate. Same model, same hyperparameters, same prompts across every method. So the only thing that changed is the algorithm.
And then there's the number that made me sit up. The paper also runs giant off-the-shelf frontier models on WebShop, just prompted, no training. In their tests, Gemini 2.5 Pro lands around 36%. A nearly 400 billion parameter model scrapes 17. And the trained 1.5 billion model with G2PO, 71%. A tiny trained model roughly doubling a frontier giant that's hundreds of times its size.
Which is the real lesson hiding in that contrast. Raw scale and clever prompting don't buy you agent skill. You have to actually internalize it through training. And the efficiency story makes it sharper still. G2PO trained agents tend to finish tasks in fewer interaction turns than the baselines, which directly cuts inference and API costs. Better policy and a cheaper one.
And now the closing flourish on the cost side, which is the line that makes it feel like a genuine free lunch. A full training step is dominated by the GPU work, rolling out attempts, running the update, hundreds of seconds. The entire graph building and advantage machinery, it adds about 1 second, roughly 0.4% of total training time. Because it all runs as bookkeeping on the CPU and never touches the GPU. It's the difference between cooking a second meal and just reorganizing the receipts you already had.
More than 20 points for less than 0.5%. That's the whole pitch in one ratio.
It is. And this is where I want to push, because the framing is confident, and there are a couple of places it's stronger than the evidence strictly supports. Start with the foundation. The entire graph depends on detecting when two situations are identical, and the paper is genuinely thin on how. It clusters identical observations into nodes, but on WebShop and the household tasks, observations are short, tidy, structured strings, so exact matching plausibly just works. Now bring in AppWorld, the hardest benchmark, where the agent writes Python and calls APIs, and observations are sprawling, messy API returns. Exact collisions should be far rarer there. And look at what happens to the margin. On ALFWorld, more than 20 points over GRPO. On AppWorld, under 3 points. The method still wins, but the gap collapses to a fraction, which is exactly what you'd predict if the graph buys you less when states rarely repeat. So the honest read is that the headline 22 points is the best case, harvested precisely where situations collide most.
That's fair, and I think the paper would half concede it. Though I'd say the fact that it still wins on AppWorld at all, where the graph idea is under maximum stress, is itself a small point in its favor.
Agreed. It's evidence the idea degrades gracefully rather than breaking. But 2 more cracks. The clean variance drops by the group size result leans on assuming each attempt in a node is independent, when the whole premise is that these trajectories share history and are correlated. The paper actually uses that correlation elsewhere to argue the edge signal stays stable, which makes the independence assumption sit a little awkwardly. So the tidy fifth the noise figure is an idealization. The real reduction is murkier. And the error bars. Some of the most dramatic per-subtask swings, a 42-point jump on one household subtask, carry standard deviations big enough that, with only 3 random seeds, a cautious reader would want more runs before banking the largest numbers. The overall improvements are far more stable, so the central claim holds. But the eye-catching subtask figures are noisier than they look. And almost no extra compute measures advantage computation only. It quietly ignores that you have to store and cluster every intermediate observation across every trajectory, a memory cost the timing chart never surfaces.
All of that's fair, and I'll concede every piece of it. The matching rule is underspecified. The proof assumptions are idealized. The subtask error bars are wide. What I'd hold on to is that none of it touches the core move. Even where the gain shrinks, the direction is consistent, and the overall numbers, not the cherry-picked subtasks, are stable.
And I'd just leave it here. The reframe is more durable than any of the specific formulas. The claim I can't argue with is that treating agent exploration as isolated lines was a modeling error. There's real graph structure in that data we'd been discarding. Whether the precise variance bound or the matching rule survives is almost beside the point.
Which is exactly the right note to land on, because the durable result here isn't the algorithm. It's the shift in what you think you're looking at. For years, the field treated sampled experience as a flat pile of independent attempts. G2PO says, no, look closer. Those attempts keep walking through the same rooms, and that overlap is free structure you've been throwing in the trash. Better signal, sharper credit, almost no added cost, all from refusing to pretend the lines never cross. Look at the graph, not the lines. That's the idea that outlives the paper.
So here's the question for you. G2PO's whole bet is that you can keep squeezing more learning signal out of rollouts you already paid for. No critic, no reward model, just better bookkeeping. So, is that the path forward for Agentic RL? Get smarter about mining the data you've got. Or have we hit the ceiling of sparse right or wrong rewards? And the next real jump has to come from denser feedback during the task. Pick a side and tell us why in the comments.
If you want to go deeper, the full annotated version of this episode is on paperdive.ai. Every technical term tapped to define, with links to the related papers grouped by theme, plus our weekly and monthly roundups.
Quick housekeeping. This script was written by Anthropic's Claude Opus 4.8. Bella and I are both AI voices from 11 Labs, and the producer isn't affiliated with either company. The paper is Group Graph Policy Optimization for Long Horizon Agentic Reinforcement Learning, posted June 22, 2026, and we recorded this the next day.
So next time your agent keeps wandering into the same room, don't log 8 strangers. Draw the map. See you in the next one.